Hi guys, so today we're going to be discussing Leetcode question 704, binary search. So given an array of integers nums which is sorted in ascending order, an integer target, write a function to search target in nums. If target exists, then return its index, otherwise return -1. It is also given that you must write an algorithm with O of log n runtime complexity. So let's say this is the example that we have. This is the nums array that we have, and this is the target that we have to search for. So in this array, we can obviously see if we do a linear search, like start from the beginning and keep on searching until we find the target, we can easily spot that target over here. But the complexity of that algorithm would be O of n, since the worst case scenario would be to traverse all the n elements of the array, and therefore the complexity O of n. Can we do any better? The question suggests to do it in O of log of n. So is that possible? And if yes, how? So there's an algorithm, binary search. So what the algorithm does is, the main idea of the that algorithm is, main idea, array must be sorted and divide array in two halves, left and right. And what do you do in those two halves? Search in left for target and search in right half for the target. Wherever you find it, just return it. So this is how, since you keep dividing your array by 2 times every time, this is a recursive call that goes back to here, and then this also goes back to here if this condition is encountered. And every time the array part is divided into half, so this ultimately leads to a log of n complexity. How? We'll discuss that later on. But for now, let's say this is the start that we have, starting index, and the end is basically the length of the array. So how does binary search work? We calculate the middle point. In this case, the middle point would be this, 0 plus 6 divided by 2, that gives us 3. So middle point is this. So we search, where does the target lie? Is target equal to the element at middle index? No. Is it less than that? No. Is it greater than that? Yes. Since it is greater than that, and we're working with a sorted ascending order array, so that means if the target is greater than the element at the middle index, so the target must lie somewhere on the right hand side of this array. So therefore we search in the right index, right half of the array, which is this, and ultimately this is how we keep on searching and then end up at this index. I'll do a dry run of this down here. So as I said, this is the algorithm. So first calculate the middle, which is this. Calculate the middle. Once you have done that, check if the element at the middle index is equal to target or not. If yes, return middle. Otherwise, if it's less than that, if the target is less than the element at the middle index of the array, so that means the target is less than that and therefore in the left half. So do a recursive call and return whatever you find in the left half of the array, which is this. Return binary search in the left half of the array. This is the name of the function. This is the name of this same function. So this is the definition of this same function, binary search. If not, then check if target is greater than nums middle. Basically, if the target is in right half or not, then return the recursive call in the right half of the array. Search in the right half of the array. So let's understand this via a dry run example. So let's pick the example that we were dealing with earlier. So let's say nums equals to, this is the array that we had, right? -1, 0, 3, 5, 9 and 12. Index 0, 1, 2, 3, 4, 5, right? This is the start, this is the end is equals to 6, right? So what is the step 1 for this algorithm? The step 1 is, the first step is calculate middle. So it calculates middle, which is 0 plus 6, 0 plus end, right? Start plus end. Start is 0, end is 6, divided by 2. This gives us 3. And target is 9. So what is the nums middle in this case? Nums middle is 5 because this is the middle part, right? Nums middle part. So 5 is less than 9, right? So nums middle is less than target. So that means search right half. And how do we search the right half? This is how we search the right half. That means from middle onwards till the end. That is what you have to search. So this is searching in the right half. So that means now this makes a recursive call to this part of the array, the fourth point. So this is essentially what we are doing here is return. I'm just writing BS, which stands for binary search. I'm just writing the abbreviation for that. Binary search, we pass the nums array, the target, which is 9, the middle plus 1, and the end. So now in this, what do we have? We now calculate again the middle, which is, in this case, start is 4, end is 6, so 4 plus 6 divided by 2, this gives us 5. So clearly nums mid, in this case nums mid would be what? This part, right? At index 5, so this would be mid. So nums mid is greater than target. How come? Because nums mid is what? 12, right? And target is 9, so 12 is greater than 9. So that means we encounter the condition searching in left half, so basically this third point. So what do we do? Search in left half. How do we do that? So we search in left half, right? We search in left half. Again, notice, what does searching in left half mean? From the middle index, from the starting index till the middle index. So that is what you have to search. So we make another recursive call, which is binary search. Again, these are the abbreviations. We pass the complete array, target, which is 9, and the new start and the new end. Start and end. End would be the middle in this case. See, so start is 4 and middle is 5. So this is what we'll pass, and this will execute in this manner. We'll compute the mid here. Mid would be 4 plus 5 divided by 2. Notice, whenever we're computing the middle, we're doing integer division. We don't have to work with float values. So this gives us 4. So now nums mid, what is that? So the new mid is basically this part in this array, right? So nums mid and target is 9, right? So are they same? So yes, in this case they are the same, because mid is 4 and the element at index 4 is 9. So 9 equals to 9. So therefore we have a match. Now that we have a match, that means we have encountered this bullet point 2 in the algorithm. Since there's a match, we return the middle. So we return middle. So this middle essentially returns to this, its calling function, which is this. Since we have a return statement here as well, so whatever is returned here, that means whatever is replaced here, in this case it would be the middle, which is 9. This would be then returned here, and this would be returned to its calling function. So essentially we found the index where we have our element, and notice that again every time we're searching in half array, we're not matching the full arrays, we're not searching the complete array. So this is how binary search works. I hope you guys understood this algorithm, and again the emphasis was on how every time we were first searching in this complete array, then we searched in right half, right? So that basically means we search from this part with this part to this part. This is our search part. And now once we had this, when we are at this condition where mid is equals to 5, so mid was this position, so we searched in its left half. That means the left half of this array. the selected array, so which is essentially this part, the index 3 and 4. So notice how we have every time we searched half array, not the complete array. So this results in log n complexity. How? I've shown that below. So the binary search complexity for this is log of n. How do we compute this? So again, as I said earlier, initially we had n elements, right? We search in, whenever we implement the first binary search, we search in the remaining n by 2 elements, because we either search in its left half or its right half. Now these are the number of elements that we have to work with. We either search in its left half or right half, which results in n by 4 elements to be compared with, then n by 8, then so on so forth, until we have a single element to return, which is basically encountering this condition where we match our element. So essentially, let's assume that we had total n elements and we kept dividing it by 2 k number of times, and after k number of times we reached a stage where we had like the one element remaining, our required element. So if we try to solve this equation, this gives us 2k greater than equal to n, and this is k greater than equal to log base 2 n. So this is how the binary search complexity is computed, and this is the proof that binary search complexity is log of n, or you can say O of log of n. So I hope you guys understood this algorithm. I hope you guys also understood the algorithm via the dry run and how it works, and how the complexity of this algorithm results in log of n. I hope you guys enjoyed this video. Keep coding, guys, and I'll leave the code for the GitHub repository in the link below, in the link in the description below. Please feel free to check that out. Thank you for your time. Have a nice day.